Okay, welcome everyone to this continuation of algebraic geometry or topology. We'll see. Well, there's essentially no difference today whether you like topology or algebraic geometry, because we are going to talk about a tautology. So what is a tautology? A tautology is a tautology. Yeah, we'll see later what a tautology is. Essentially, tautological sheaves are tautological sheaves. So yeah, what I'm trying to explain today is a little bit like what is a sheaf of modules, why is it important, and give you an example at the same time. Yeah, and it turns out that sheaves of modules is a notion that you might have seen in topology, because essentially algebraic geometers and topologists did it at the same time under different names with slightly different settings, but they're essentially the same. And I'm trying to motivate this now from the point of view of topology, because algebraic geometry is in the end abstract, so it's much more difficult to motivate. It's then somehow easier to compute, but somehow more difficult to motivate. So let's start by a bundle. So a vector bundle is essentially a sheaf of modules. Let me explain the terminology for a second. So sheaf of modules, right, was this idea to associate a module to every open set. That's what a sheaf does. What is a module? Well, a module is essentially just a vector space. It's just a fancy name for a vector space plus. A vector space plus a vector space with something extra, like a group action or something. In this case, an action of the corresponding ring. But anyway, so it's a vector space plus. And a vector bundle is vector spaces. So that's where all the names come from. So it's essentially the same. They're essentially the same idea. So here you associate, let's just say, a vector space. Let's just make it easy. A vector space to every open subset of a space, such that it kind of glues nicely together and you get a new type of object which is like your original space. And in a vector bundle, you associate a vector space in the very same way to every point, such that the object in kind of a continuous, nice way, such that if you vary it, you get kind of a new object, a collection of vector spaces, which is like the object you started with. So it's really type of the same idea. It's a bit nicer in topology. Topology is always easier to motivate somehow. You can draw a nice picture. In abstract algebraic geometry, kind of the idea is not to draw any nice pictures anymore, which is a bit annoying and a bit powerful at the same time. Anyway, so a vector bundle is essentially a linear algebra generalization of a cylinder. A linear algebra generalization of a cylinder. Say that again. We're talking about vector bundles instead of sheaves of modules, but they're essentially the same thing. Okay, we come back to sheaves later. For now, a vector bundle, you have some space, yeah, like here, and a line, and to each point you associate a vector space. What is a vector space? Well, let's say a one-dimensional vector space, like a line. So for each point you have a line, and those lines kind of vary continuously with the space, and you get a new space like this type of thing. Well, this is probably a bad way of doing it. This type of thing here in the background is kind of the new space, and it's like the vector bundle. It's like a cylinder over your space, right? If you think about your original space being a circle, and then you attach to every point like a ray, because that's a one-dimensional vector space, what you get is like an infinite cylinder. But there is some global property, some local gluing property involved, and globally it doesn't need to be a cylinder. For example, the Möbius strip is also a vector bundle over the circle, where you just, well, you glue them together in a certain way, and you can glue them together a little bit twisted, and you get the Möbius strip. Strictly speaking, you kind of get like the infinite cylinder and the infinite Möbius strip, because well, a line is kind of an infinite thing, but let's ignore that. So really the idea here is, to every point in our space we associate a vector space so that they fit together in a nice way and to form another space of some desired type, whatever our desired type is. Maybe we are topologists and we like manifolds. Maybe we're algebraic geometers and we like varieties. Maybe something else, right? And that's like the whole idea of this thing. Like, is to associate a vector space, linear algebra, in a way such you get a new object consisting of vector spaces. Now, essentially, the points are now vector spaces that kind of forms the same type of space, variety, manifold, whatever it is. And sheaves of modules and vector bundles are essentially the same. Right? The same idea. You associate a vector space to a point or to an open set, or maybe it's a little bit more difficult than a vector space, maybe it's a module, but essentially that's the same idea, and that's why they are so important. So topologists study vector bundles for a long, long time. Again, it's essentially a new space made of vector spaces, and everyone likes vector spaces, and everyone likes new spaces. I'm not sure whether everyone likes vector spaces. I'm pretty sure nobody likes vector spaces, but I like vector spaces, which is now a contradiction. I'm very confused. Vector spaces are liked by a lot of mathematicians, probably not by a lot of people, but by a lot of mathematicians, and mathematicians came up with this idea of putting vector spaces to points such that they form a new space, and usually call it a vector bundle or a sheaf of modules. Depends a bit whether you're a topologist or an algebraic geometer. And this is my alternative motivation of sheaf of modules. Like, it's like the vector bundle analog in algebraic geometry. So it kind of hopefully makes some sense. And kind of a key example I would like to have in mind is the tautological bundle. So you need to associate a vector space to every point. But we already had something that had parameterized vector spaces, the Grassmannian. The Grassmannian, the set of k-planes in whatever, r to the n or whatever you want. So every point actually is already a k-dimensional vector space. Yeah? And the standard examples here were projective space, for example. It would be one-dimensional subspaces and an n-dimensional space. But you kind of can have whatever, 4-dimensional subspaces and a 15-dimensional space, or whatever. But the points of a Grassmannian are already vector spaces. And essentially, by definition, by having this upper triangular form, this echelon form, essentially they vary continuously already. Yeah. So that should be kind of, by definition, by its existence, by its very existence, should be already a vector bundle. Essentially, the vector space you associate to every point is just the vector space that sits at that point already. Yeah, and that's what will be the tautological bundle, right? Tautological bundle, we already have a vector space sitting at that point, so why don't we take that vector space sitting at that point? And that's like the tautological bundle. It's kind of a standard example, a kind of nice example, but a little bit tautological, obviously, of a sheaf of modules. So essentially, sheaves are vector bundles. If you want to have a more precise statement, here's one that you can do. So a section of a sheaf is essentially a way to find your original space in the new space. So my original space is like a line. Here's a section. It's just some way of putting your original space into the new space formed by the vector spaces. That's called a section. And the sections form a sheaf. You can always associate the sheaf to a vector bundle, the sheaf of sections. And the other way around, every vector space like sheaf, locally free, that's kind of the terminology you use. Every vector space like sheaf comes from a section of a vector bundle. So they're essentially the same object. So the games you should be able to play with vector bundles, and the games you should be able to play with sheaves of modules, they should be somehow very similar, right? So they should be somehow very similar. So there should be a tautological bundle, a tautological sheaf over the Grassmannian. And yeah, there is. You just do the same. I will do it more formally for P1 in a second, because there's kind of a fun alternative definition. But essentially what you have to do, I just do the topology definition here. It's really just a tautological bundle of G, N, K. Probably it was Kn before. Doesn't really matter, but anyway. So N is the parent space and K is the dimension of the vector space I am using. So K equals 1, for example, is just so-called on P1. It's kind of the tautological line bundle on P1, where P1 is lines in a space. So what is your line bundle? You attach the lines that you already have to your points, which are the lines. Tautological. In case you don't know what the tautology is at this point, doesn't matter. Let's have a look at it. XKCD comic, or a web comic, right? So XKCD is kind of a web comic explaining what a tautology is. And the only thing you actually need to know is that the first rule of the tautology club is the first rule of the tautology club. Yeah, so tautology is somehow kind of something that is true, whatever, no matter what you do. Kind of fun thing, for example, if someone asks you, can I ask you a question? What you should answer is, you're very funny, that is a tautology. I do that all the time, people get very confused. Maybe you don't want to try that out. But essentially, if someone asks you, can I ask you a question? They already answered their own question. So it is, in some sense, a tautology. Anyway, tautological really here just means, I mean, we already have vector spaces, right? So we just put them onto the points. The reason why I'm not doing this more formally is that there's some boring subtleties that I'm going to ignore. There's not really an issue anywhere, but yeah, there's some subtleties and nothing serious. I'm going to ignore them. Let me rather give you an alternative definition in the case k equals 1. Alternative definition means whatever I'm going to write down now will be isomorphic to this tautological line bundle or the corresponding sheaf. Yeah? But it's not quite obvious. It's kind of an exercise. So in a lot of algebraic geometry books, you will see that as an exercise. I just take it as a definition. So here comes now the definition in the special case. K equals 1. Same target but colored. So essentially you do the following. It's kind of a fun trick and it's good to know that this exists anyway. So whenever you have a projective variety, projective varieties are nice because their corresponding rings of regular functions are graded rings. Right? These are kind of homogeneous polynomials, if you want. So they are graded rings. For graded rings, what you should do is you actually should study graded modules. So graded representations, graded modules. In particular, you can just act on yourself. You can always do that. You can act on yourself, but shift it. Maybe instead of saying a polynomial of degree 3 is of degree 3, you just say it's of degree 5. Then you shift it up by 2. Or you say it's of degree minus 12. Then you shift it up by a number that I can't compute. I shouldn't have said minus 12. Maybe you say it's of degree 1. Then you shift it down by 2. So there's a way to just associate a sheaf, very tautological again. Namely, you just act on yourself. You just shift yourself around. No? That's a sheaf of modules just shifted around. And it usually has like a name. It's this funny OD, where D is a shift. So if you shift it up by 2, it's 2. If you shift it down by 1, it's minus 1 or something like that. And that's also very tautological. And the only thing you need to make sure is that kind of the shifts work out. And the minus 1 version for P1 is like this tautological bundle over P1. It's also called the twisted bundle. I'm not quite sure where the name twisted comes from. I would rather say regraded bundle. But these guys are called twisting sheaves. Again, I don't quite know where the name twisting comes from. For me, it's a recoloring, right? Grading is like a coloring. Your polynomials have degree 3. Your polynomials have color green. And you kind of change your coloring, right? You go from green to red to orange or something. So, but it's essentially still the same type of object, but somehow just recolored, right? So that's kind of the point. And then you get a new sheaf by just recoloring everything. And yeah, and if you color it down by 1, it turns out that you get the tautological one on P1. And that would be kind of the formal definition. As I said, this is usually an exercise, show that the tautological bundle on P1 is isomorphic to the twisting sheaf minus 1. But I just take that as a definition. Okay, I hope you enjoyed this video, and I also hope to see you next time.